Hello everyone. Have you ever noticed how your electricity bill doesn't rise just because you plug in a fan and a tube light together, even though both draw alternating current? That's because not all current in AC circuits contributes to real power. Let's begin with the basics. The voltage across an AC source is V of t equals Vm sine omega t, while the current is I of t equals Im sine of omega t minus phi. Multiplying them, we get instantaneous power P of t equals Vm Im sine omega t times sine of omega t minus phi. After simplification, it splits into two parts, one steady term proportional to cosine phi and another rapidly oscillating term with double frequency. The oscillating part averages out to zero, leaving only the steady contribution to average power. Hello students! Let's now explore how the phase angle plays a crucial role in power consumption in AC circuits. The average power over one cycle is given by P equals Vm Im divided by 2 multiplied by cosine phi. This can also be written as Vi cosine phi. Notice that only the cosine phi term decides how much of the apparent power actually becomes real power. Another way to express it is P equals I squared Z cosine phi, where Z is the impedance of the circuit. Here, cosine phi is called the power factor. It tells us the fraction of the total or apparent power that is effectively converted into real, usable power. For example, if the power factor is close to 1, it means almost all the power drawn from the source is being used effectively. But if it's low, a large part of the current is wasted in merely sustaining reactive effects of inductors and capacitors. That's why industries and big consumers always try to keep a high power factor, because higher power factor means more efficient power usage, lower electricity bills, and reduced energy losses. Quick insight: improving the power factor is like making sure every drop of fuel in your car contributes to moving it forward, rather than just heating the engine. Hello everyone. Now let's talk about how the power factor behaves in different AC circuits. In a purely resistive circuit, the phase angle phi is 0. That makes cosine phi equal to 1. Voltage and current are exactly in step, and we get maximum power transfer. In a purely inductive or purely capacitive circuit, the phase angle phi is pi by 2. That makes cosine phi equal to 0, which means no average power is delivered. The current is called wattless, it just oscillates without doing useful work. In RL, RC, or RLC circuits, the phase angle lies between 0 and pi by 2. So, only a part of the current contributes to real power, giving partial power dissipation. Finally, at resonance, when inductive reactance equals capacitive reactance, phi again becomes 0. This makes the circuit behave like a pure resistor, and maximum power is dissipated across R. Quick insight: remember that only the resistive part of a circuit consumes real power. Inductors and capacitors may look busy, but they don't add to your electricity bill. Have you ever thought about why in alternating current circuits, not all of the current actually contributes to useful work? Let's break this mystery into simple parts. The total current in an AC circuit can be split into two components. The first is IP, equal to I times cosine phi. This is the component of current that stays in phase with the voltage. It is the real or power component because it contributes directly to useful power. The second is IQ, equal to I times sine phi. This is called the quadrature component and it is wattless. It does not produce any power loss, but it constantly exchanges energy with the circuit's magnetic or electric fields. Now, when you look at the phasor diagram, you see the current vector split into these two parts, IP along the voltage axis and IQ at right angles. And here's the key point: only IP contributes to real power. That's why the real power is given as P equals IP multiplied by V. Quick insight: think of AC current as a team effort. One part does the real work, the other just plays support by storing and releasing energy, but together they define how efficient the circuit really is. Hello everyone. Have you ever wondered why electricity boards often insist on maintaining a good power factor? It's not just a technical detail, it's the secret to reducing energy wastage and saving money. When the power factor is low, the transmission current becomes unnecessarily high. That means large I2R losses, wasted energy in the form of heat in wires. The practical solution is smart. We add capacitors in parallel to the circuit. These capacitors supply a leading reactive current, which cancels out the lagging component caused by inductive loads like motors or transformers. As a result, the effective current shifts closer to being perfectly in phase with the voltage. This means less wastage, less heating of lines, and more efficient use of power. In fact, this method is widely used in power systems, industries, and even big buildings to reduce losses and improve efficiency. Quick insight: a capacitor bank in a factory is like a fitness coach for electricity. It keeps the current in sync, reduces wasted effort, and ensures maximum efficiency in every workout of the power system.
Hello everyone! Let's take a practical example to connect theory with calculation. Imagine we are given an AC source with peak voltage 283 volts, frequency 50 Hz, resistance 3 ohms, inductance 25.48 millihenry, and capacitance 796 microfarad. Step 1. Let's find the reactances. Inductive reactance XL equals 2 PiFL, which comes out to about 8 ohms. Capacitive reactance XC equals 1 divided by 2 PiFC, which works out to about 4 ohms. Step 2. Impedance. The formula is Z equals square root of R squared plus XL minus XC whole squared. Substituting values, we get Z equal to 5 ohms. Step 3. Current. RMS current, I equals V RMS divided by Z. Now, V RMS is Vm divided by root 2. So 283 divided by root 2 upon 5 gives nearly 40 amperes. Finally, step 4. Power and power factor. Power P equals I squared into R, which comes to around 4,800 watts. Power factor cos phiI is R divided by Z, which equals 0.6. So, this example shows how reactances, impedance, current, power, and power factor all connect together in an LCR circuit. It's like the entire chapter condensed into one neat calculation. Quick insight: the power factor here being less than 1 tells us not all the supplied power is converted into useful work. Some is lost in reactive effects. So to sum up, the real power in an AC circuit is P equals VI cosine phi. The power factor cosine phi is the key efficiency measure. Purely resistive circuits have unity power factor and consume maximum power. Purely inductive or capacitive circuits consume no net power. Most practical circuits lie somewhere in between. Improving power factor is crucial for reducing energy waste in industries and transmission lines. And remember, wattless current may not cost money directly, but it increases current in the lines, causing unwanted heating losses. I hope this session helped you see how the power factor connects the geometry of phases with the economics of electricity bills. In the next discussion, we'll explore resonance in detail and see how LCR circuits selectively respond to specific frequencies. See you then!